So quickly, I'm going to ask each one of you as we go along. Blue teddy. Imagine there's a blue object and have blue light on it. What color is it going to appear to be, Yasser? Yes, you're awake?
Just blue. Yeah.
Perfect.
It's just gonna be blue.
Blue. Okay, good. Marco, if I have a blue teddy and green light on it, what color is it going to appear to be?
A blue teddy and more?
And green light. Let's say I've got a blue teddy bear.
Oh, it would be black.
Bear, perfect. Ahima, green camel, red light. What color am I going to see the camel as?
Black.
Excellent. I've never seen a green camel, but it's an interesting concept. Okay, Ajay, blue light and green camel.
Black.
Excellent. Huzaifa, green light and green camel.
Green.
Okay, I'm not going to torture you guys anymore with any more of this. You guys clearly understand it, okay? Let's move on. Right, translucent and transparent, another very important concept. If you're doing OCR, you'd have learned some of this in year 7 and year 8. If you're doing AQA, you learn it now in year 10 and 11, so, or year 9 even. So let's look at this. Get the title down, guys. Can anyone tell me the difference between something that's translucent and transparent? No one's sure.
Transparent is see-through, and then
Yes.
translucent is partially see-through.
Okay, that's a good start. Okay, that's a good start. Translucent is partially see-through and transparent is completely see-through. So you'd say transparent is like a glass window made of normal glass, and translucent might be a glass window that's colored. Would you say that?
Yeah.
Okay, we're going to explore that definition, yeah? All right. A transparent object is one that lets all the light through. For example, glass, it lets everything through. A translucent object is one that lets light through but absorbs or blocks some of it. For example, colored glass, like a filter, yeah? What this is going to do is going to block everything except blue light. So now these definitions are coming from our understanding of what different colors do to light. So we're building up our understanding. So I want you guys just to make sure you write that down, yeah? So when you're using a camera filter to take a picture, you're actually filtering out certain types of light, and this makes your face appear to be of a different tone or a different, it shows a different amount of radiance from it. So this is important, the definition or the difference between transparent and translucent. Okay, we don't need any examples yet, don't worry, just need to, for translucent anyway. We just need to know what it means, and we need to know what this means. So example could be colored glass. Yeah, if you want. For translucent, you could put colored glass in. Colored see-through object, they all work. Okay, gonna move on. If you guys are okay with it. Okay, let's move on. Right, black body radiation. Can anyone tell me what black body radiation is? I'm not sure. We'll come back to it. I'm going to come back to black body after. Now, let's look at the basics of radiation here. So this is going to be good for some. We're going to come back to black body in a bit. We're going to talk about a lot of interesting things now. Okay. So radiation, first of all, is energy emitted by objects. Objects might emit energy in different forms. And when you're emitting energy in the form of waves, it's called radiation. The sun emits radiation. Why? It emits light, which is a form of energy in the form of waves, and heat, which is energy in the form of waves. Now, we need to understand, we're going to go back to black body radiation now. We need to understand the difference between what a black surface and a white surface does to radiation. Black surfaces love to absorb heat. White surfaces love to reflect heat. And we touched on this last week. And so the white surface will reflect the wave of light that comes to it. The black surface will actually just take it in, and you'll get warmed up because it will absorb. Right. So all bodies or objects emit and absorb radiation. Everything you see around you lets out radiation. And everything you see around you absorbs radiation. Everything absorbs heat to some degree, and everything releases heat to some degree. The hotter the body, the more radiation it reflects or radiates every second. If you look at a video like this, because this lesson can get boring if we just look at the same thing. If we look at how police work, they use radiation to catch criminals. Can anyone tell me more about what I'm about to say to you? Can anyone guess how radiation can be used to catch a criminal? I'm going onto a YouTube video to show you. Okay, so basically, let me show you. Police infrared. Yeah. What a person's body does, because we are warm as human beings, we release radiation. Let me forward this. Okay. Okay. You can see the police helicopters looking at the ground at night. At night time, you don't have much light. This camera they're using is what we call an infrared camera. So things that release more heat appear to be brighter in this camera, and things that release less heat appear to be less bright. Okay. Even the trees release some heat, which is why they have some brightness. They're dark, but they have some brightness. Houses have kitchens and rooms and people. They release more heat, so they appear to be a bit brighter. The car, look at the car, for example. I'll show you a car in a second. Look at the cars over here. The car underneath it is bright. There's no lights underneath a car. Why is it bright? Because the engine's releasing heat, and this appears to be bright. So everything's releasing or absorbing heat to some extent. Once this car goes on and on, let me turn the volume down. You'll see that someone's going to jump out in a second and start running. A person running through the dishes, this person's got a gun on him, you can see, or her, is releasing heat. So look, amongst the trees, because the person's releasing more heat than the trees, he appears like a sore thumb and sticks out. So all objects release some type of heat, yeah? I want you guys to write this down. All bodies, anything you find, either do one of two things. They either emit or absorb radiation. They usually do both. The hotter the body, the more radiation it radiates every second. Write that down, guys. So you've written the title, Radiation, the Basics, and hopefully you've written this sentence. Marco, how far are you in your sentence? Just going to ask out of interest. Marco, you done it? I think Marco can't hear us, no problem. Ahim, how far are you?
I'm writing the red box.
Okay, cool. I'll give you a few seconds. So the red box is important, guys. And once we do this red box, there's not a lot left in electromagnetic waves. We'll be finishing that very soon. Then we'll be killing off or finishing off sound waves to be more appropriate. And then we'll be practicing exam questions. And after that, you will not need, hopefully, any more revision on this topic. Okay, so I'm going to move on in 5 seconds. If anyone wants me to leave it on, tell me. Let's move on. Okay, so black body radiation. This is an important one. And I'm going to get you guys to have a guessing game here, yeah? I want you guys to write this out and try and fill in the blanks with what you can, or leave them empty if you don't know, and we're going to go through it. Okay, so another discovery activity for you guys. Go for it. As soon as you're finished, please tell me. Anyone who's finished.
Done.
Done. Okay. So as I talk through it, you guys can start putting down definitions, yeah? So a black body, it's a special name. It's a special name for something that absorbs all of the radiation incident upon it. So all of the radiation that goes on it, it absorbs it. It's very interesting how a black body does that. Any type of radiation that goes on it, it will absorb it. It won't let anything escape, okay? A black body does not reflect or transmit any radiation. This is why black objects appear to be black, because they absorb all of the radiation and they don't let anything out. So a black object will never appear red, it will never appear blue, it will only appear black. Even though white light is shining on it, white light, there's no black in white light. However, when it shines on the black object absorbs all of the white light, and therefore it appears black. So a black body does not reflect or transmit any radiation. Doesn't let anything go through. It doesn't let anything be reflected. It simply absorbs everything. It's like someone who eats everything. Yeah, nothing gets left, which is a good thing sometimes. However, as every object also emits radiation, it follows that a perfect black body will also be the best emitter. So what it means, if something we said earlier, everything absorbs radiation, everything emits it. So a perfect black body ideally should be able to absorb radiation, and it should also be able to emit it as well. Once it absorbs it, it should be able to kick it back out, which is very weird, but it's just the way they define it, okay? So we'll say that again. A black body is defined as a body that absorbs all of the radiation on it. A black body does not reflect or transmit any radiation. So it doesn't reflect it, it doesn't transmit it. Emitting is a different thing. Transmission is going through. Reflecting is going on and bouncing off. Emission is different, and we'll talk about that. However, as every object also emits radiation, it follows that a perfect black body would also be the best emitter. So what we mean by emitter is when something absorbs radiation, even though it's not reflecting it, even though it's not letting it go through, once it absorbs it, it stores it up, it will then push it back out, it will emit it. So a perfect black body should be able to absorb radiation and push it back out. It will never reflect it, it will never transmit it. Radiation will never be reflected off it, will never go through it. However, once it's absorbed, it can push it back out if it's a perfect black body. So this word black body is the first time some of you are hearing this. And as long as you understand this and what it's saying, your definition's okay. What do you guys? I'm going to move on if you guys are okay, yeah? If you're still copying, do let me know. I'll keep it there. Okay, so I think we're okay. If you ever feel we're going too fast, just let me know as well. So color versus temperature. This is an interesting one. I'll show you a video on it to make it a bit more interesting. Where did you guys watch it? Why? What? Okay. So melting spanner with electricity. I like this video. It's quite interesting. So notice what happens to the color of this object as you put electricity through it. I'm going to skip a lot of it because a lot of it's just long and boring. Oh, this is the right, we're still not learning about that. Now watch this. If you have a, interesting. Look at what happens as you increase the temperature of this spanner. So what we're going to do to this spanner, I'm going to connect a wire here and a wire here. I'm going to make it so that electricity can run through it. But I'm going to make so much electricity run through it that's going to heat the spanner up. You can guess what's going to happen. As I connect this side, and I'm connecting it to a car battery, which has a lot of electricity for a spanner. As the electricity goes through, it'll heat the spanner up. As it heats the spanner up, notice what happens to the color of the spanner. First, you can see here, look, it's got a purplish bit. And then it's got an orange bit as well. Look at this side of the spanner, a purplish bit and a greenish bit. Yeah, if you look at it slowed down, it's really interesting. As it develops, look, this orange, this purplish bit has a white bit behind it. Here, there's still a purplish bit. As it heats up even more, that bit that's purple turns orange on that side. Here, it's gone white hot. As it carries on, you can see the heat spreading through. And look, you've got almost orange here and bright white over there. And then as it carries on, super bright white. What do you notice as it's getting hotter? The color's changing, yeah? Heat. The hotter something is, the brighter it usually gets until you've melted an entire spanner just using electricity. Very interesting how that works. So, color versus temperature is what we're looking at. How does the color of something change with its temperature? So there is some note taking here. I'll let you know. So let me read it out to you first and explain a bit, and then you can summarize this, yeah? All objects emit radiation of some kind. Anything you look at sends radiation out, including human beings, as we saw in the police video, including that spanner. As we heated it up, it sent out some radiation. Even before the spanner was heated, it was sending out some type of radiation, which we couldn't see clearly, but it was there. The color of the radiation depends on the object's temperature. A good example is a Bunsen burner in the classroom, yeah? Yellow flame and blue flame, I'm sure you've already all seen this. Most of you probably know that the blue flame is hotter than the yellow flame. So as the flame gets hotter, it becomes brighter, it becomes closer to white. As the flame becomes cooler, it becomes closer to yellow. So blue is a higher frequency than yellow light. Objects that are blue hot are often hotter than yellow hot. This is because the object emits a higher proportion of wavelengths at shorter wavelengths. So I'm going to explain this to you. It looks complicated, but it's not. So what they're saying here is, as you get hotter, you're releasing, because blue light, if we looked at, remember the rainbow earlier, blue has a shorter wavelength than yellow, and yellow has a shorter wavelength than red. If I go back a few steps, look at the rainbow colors we looked at, yeah? We said, look, if I go back to the prism, it's gonna, wow, I need to go back a bit more here. So let's go back to it. Where's the prism? We look at a prism. If we look at red light, it's got the longest wavelength. If we look at blue light, it's got a shorter wavelength. The hotter something gets, the shorter the wavelength of light gets that it gives out. So a Bunsen burner that's yellow is not as hot as a Bunsen burner that's blue, because a yellow Bunsen burner gives out yellow light, which has a longer wavelength. Okay, longer wavelength means lower frequency, in case you don't remember from last week. The blue light has a shorter wavelength, which means a higher frequency, more energy. So as your Bunsen burner gets hotter, it gives you a wavelength that's shorter or has more energy. I'm going to write all this down in a minute, yeah? So don't worry. So let's go back to our slide. Okay, so what they're saying here, blue is a higher frequency than yellow light. It's got a higher frequency and importantly a lower wavelength. Objects that are blue hot are often hotter than yellow hot. This is because the object that's blue hot is emitting more blue wavelengths. So emitting a higher proportion of wavelengths at shorter wavelengths. They've made this confusing. It's just what they mean here is just emitting more blue wavelengths. Before you copy this, I'd like to write some notes down in my own words for you guys to understand, yeah? Okay, these are going to be important notes. So, right. Wavelength, frequency, and energy. These three things, I need you to copy this down. Wavelength as your title, frequency as your second bit, and energy as your third bit. Now, let's compare two things. Let's compare red, which has a longer wavelength, and blue, which has a shorter wavelength. You can see blue, the distance between two peaks, the wavelength here, for example, lambda, is much shorter than the distance between two peaks there. So what we can say here is, in black, we write, as the wavelength of electromagnetic radiation. Remember, light is part of the electromagnetic radiation family. As the wavelength of any electromagnetic radiation, including light, so at the wavelength of electromagnetic radiation increases, so as the wavelength gets bigger, what's going to happen to frequency? It's going to happen, the opposite is going to happen. The frequency will decrease. The amount of waves going past the point every second will decrease. Imagine these two are traveling at the same speed. If I have a point here, more of this is going to get past the point. If I draw a point here and a point here, more of these waves will get past this point in 1 second than these waves will, because they're longer. So as the wavelength of electromagnetic radiation increases, frequency decreases. And we need to remember now that frequency is proportional to energy, meaning As frequency increases, energy increases. As frequency decreases, energy decreases. So what we say is that, right, in simple terms, because frequency decreases, energy will increase. Because frequency decreases, energy will increase. Okay, let's look at an example. Increase. So our example is going to be the Bunsen burner, e.g. a cooler Bunsen burner, has a yellow flame, whereas a hotter Bunsen burner, will possess or will have a blue flame, will possess a blue flame. How can we link this to what we've learned? We'd say yellow, if I draw it down here, I'll draw a yellow color to give us a visual understanding. You can probably already guess what I'm going to do. Yellow has a bigger wavelength here than blue, which we already know about. We know what blue does. Blue is shorter than yellow anyway. So I'll just redraw the blue as well to give us a really good, solid understanding. So we can say here, look, yellow, let's write in black so you don't get confused. We say here, yellow equals longer wavelength, lower frequency, less energy. Longer wavelength, and we'll write in brackets, which means, we'll write after a comma, lower frequency, which means lower energy. So the flame is not going to be as hot. It's giving yellow light out. But blue, we already know, blue, shorter wavelength. And when you have a shorter wavelength, the frequency is always the opposite. The shorter your wavelength gets, the frequency will be opposite. Inversely proportional, we call it. Shorter wavelength, higher frequency. And the higher the frequency, more energy. Okay, so once you guys copy all of that down, we can go back to our PowerPoint. Okay. Marco, can you understand handwriting? Marco, are you there?
Yeah, hello?
Yeah, hello. Can you understand handwriting, Marco?
Yeah.
Perfect. Okay. How far down are you, Yasser?
Done.
Done? Excellent. Audrey, you done?
Yeah.
Okay, good. I'm going to ask one more person. Ahim, how far down are you?
I'm done.
Well done. Well done. So, Mark, are you done?
Yeah.
Perfecto. Huzaifa's going to be done because I know Huzaifa's speed, unless Huzaifa tells me different. Okay, so we're going back to this understanding now of why different colors are linked to different wavelengths. So now you know yellow and blue. Blue is a higher frequency than yellow light. Objects that are blue hot are often hotter than yellow hot. You know this now from my notes. This is because the object emits more blue than yellow. They haven't written this really well. That's why we wrote it in our own words. The same applies to stars. So the sun and a blue star. Which star is hotter, Hema?
The blue star.
Well done. So this blue star is probably, I'm guessing here, thousands of times hotter than our sun. If we went close to our sun, we'd melt. Before we even got close to this, yeah, if we went close enough to this, we would also melt. You'd need to be less close to this one than to the sun to melt. You could be really far from the blue one and still melt. Some stars are even hotter than the sun. Some stars even get hotter than this blue star over here. So all of these blue stars we see in the sky, they're hotter than our sun. They're so far from us, we can't feel their heat. And that means you can imagine the sun's 93 or 96 million, if I remember correctly, miles away from us. 96 million miles away. That's far. 96 million miles is no joke, yet we feel its heat. This star that's millions of times hotter than the sun, we're not feeling its heat. Imagine how far that must be. The universe is massive. Okay, so we've got approximately 15, 20 minutes left. If you guys want a 2-minute, 3-minute breather, just let me know. I don't mind. In fact, what we'll do now, we won't have a breather, but you can use it to your advantage. Those of you who want to breathe for the next 3 minutes, use it as a breather. But my recommendation is I want you to read over everything we've done today and so your brain can consolidate. So I'm going to give you 3 minutes to do that. Read over everything you've done today. If you haven't read over everything from last week, maybe start from there, just to get up to date with what we're doing. 3 minutes, guys. So we're going to be back we're still here, don't go anywhere. At 17:59, I'm going to start again. So 3 minutes, read whatever you can. We've got 2 minutes left. Just consolidate all of our knowledge. Thirty more seconds, guys. Okay, so now that you've had a bit of time to read over what you've done, if you have any questions so far, ask me as well, yeah? Sometimes when you're learning a lot of stuff, I like to have little mini breaks in the lesson, so you guys can just read over stuff. And if you need more time, you can always ask. Okay, so temperature and balancing radiation. What we're going to do, we're going to look at a lot of things now. So we've got only 2 slides left before we go into sound, yeah? So we're nearly finished with everything here. Now, this is an important thing. Before we write anything, let's look at our house, for example. In your house, as a builder in the modern day, with the current day situation regarding pollution and the environment and the importance of saving energy, you need to build a house that is efficient in terms of energy. You want to build a house that you're not wasting energy from. It's not, energy is not escaping, heat's not escaping outside, so that you need to put your heaters on for longer. Your house should be able to trap heat well, so that you can efficiently heat it up and not lose what you're spending on heating. So my house is nice and warm, for example, 20 degrees Celsius. In a normal house, it will be, yeah? Right. So outside it's going to be cold. Whenever there's a difference in temperature, heat will always try and escape. If you open your window on a cold day and your room's nice and warm, it's not that the cold's coming into your room. Cold doesn't move. Heat is what moves. It's that the heat is leaving your room. So whenever there's a temperature difference, heat will move. It will move towards the colder area. Heat's just like that. Right. So the temperature of the house depends on how much heat is escaping and how much heat is being made. So the house is going to make heat and emit it. It's going to cause it to escape, yeah? As it does that, it will get cooler. So you've got to figure, you've got to, for a house to stay warm, you've got to prevent the escape. This slide doesn't do a very good job of explaining that, so that's why I'm discussing it. There's not much to copy here right now, so don't worry, okay? We're going to talk more about that through exam questions later. Just want to introduce you to it. Now the last slide, before we move on to sound, is about the temperature of the earth. We spoke about this. So the temperature of the earth depends on many things, including how much energy is absorbed from the sun. The earth absorbs and reflects energy. The sun's waves come, they come into this earth. So this wave from the sun is coming from somewhere. It's going to go to the atmosphere. Some of it's going to be reflected off, just like a mirror. Some of it's going to go through and come to the earth and reflect off the ground. Some of it's going to be trapped and absorbed by the earth's atmosphere. Some of it's going to stay there and cause the earth to warm up, like we looked at earlier. So energy from the sun. Some of it gets reflected into space. Some of it gets trapped in the actual earth itself. Again, so that's nothing to write about now, because we've spoken about this before. It's just a recap that what's happening with mirrors or what's happening with lenses and other things, light's reflected, some of it's trapped, can also happen with the earth. The earth is like a lens in a way. It lets some things through, it lets some things reflect, and it traps some things. So just be aware of that. Now, good news is, we've basically finished the PowerPoint. Less good news, or extra news, is that we still need to do sound. We have 13 minutes left for the lesson. What we'll do, we'll start sound off, okay? So we're going to start sound, which can be quite interesting. And it's not too long. We'll probably finish sound next week. Now, I haven't asked you many questions yet to test your understanding, but we'll come to that. So look. Now, let's recap. Let's recap a little bit. Can somebody tell me, and I'm going to write it here. Okay. I'll write a new slide. What's the difference between a transverse and a longitudinal wave? So there's I'm just going to draw a transverse wave there. That's what we've got, a transverse wave. Transverse. And longitudinal, I'm just going to represent it using long and short straight lines, for example. Longitudinal. Ohima, do you know about the difference between these two? You there, Ohima? Oh, somebody's disappeared. I think Marco's disappeared. He should be back in a minute. Okay, Ohima, do you know the difference between longitudinal and transverse?
Don't longitudinal waves have like parallel vibrations?
Oh, yes.
And transverse waves have perpendicular vibrations.
Beautiful answer, beautiful answer. So a perpendicular wave might be traveling in a forward direction. As you can see, this wave's traveling forwards, yeah? However, the waves, the energy is going to be either up, so it's going to be, if you're in a boat in the ocean, your boat will go up and down if it was wavy like this. Why? Because the energy of the wave is either up or it's down. So this is up, here's down, here's up, here's down. And you can see the direction or the angle between the wave, the direction the wave is traveling in, and its energy is 90 degrees. So in a transverse wave, you have perpendicularity. And what do we mean by perpendicularity? They're perpendicular. You have perpendicularity between the travel direction, the propagation, the progress, the way it's moving, and the displacement or energy. Does that make sense, Ahima?
Yeah.
Excellent. In a longitudinal wave, what's going to happen, it's like a slinky spring. If I put a slinky spring up and down, the energy of the spring is going to go up and down, but the waves are going to travel towards my friend who I'm going to be attached to via the spring. So I'm here, I've got a slinky in my hand here, another person's there, we're waving it between us. Energy is going up and down, but the thing is overall traveling in a forward direction. In longitudinal, what I'm doing, I'm not letting my energy go up and down. I've got my slinky spring on the ground, let's say, and I'm pushing it forwards and pulling it backwards. And what I do when that happens, if I push it forwards and pull it backwards, the energy is not going to go up and down, impossible. It's going to travel through, yeah? And as I'm pushing it backwards and forwards, the wave is moving, the whole thing is moving back and forth. The whole spring is moving back and forth. So the travel of the wave is moving back and forth, and the energy through it is also going in the same direction. They're both going in the same direction, but they're parallel to each other. And this is longitudinal. In a longitudinal wave, the energy is in the same direction as the progress. So good, you've understood that. Now, all of us have, hopefully. A sound wave is longitudinal. Why? Because in sound, what we're doing, and this is just a long introduction, which is hopefully making it interesting, or making it more understandable, more importantly. If I'm speaking to someone, and I shout at them, my sound goes to them, travels to them. It doesn't go up in the air and then down and then up and then down. It travels in a straight line. So when I'm speaking to someone, my sound travels in a straight line. Why does it do that? Because between me and that person there's air molecules. And my sound uses air as the boat on which it travels. Yeah, it's like air is a vehicle for the sound to travel. As I speak, what happens, the air in front of me gets pressed. All of the air molecules get compressed. And that energy causes other air molecules to go far apart. It's weird how that happens. And that energy keeps on going and compresses other air molecules. So the energy is doing compression and expansion, compression and expansion. So this compression, yeah, let me just write that out. You don't have to copy this, guys, just an explanation. This compression is known as a compression. The expansion has a special word. Does anyone know what this expansion bit is called? Anyone can say it. Josepha, what's the expansion called? Do you know?
Sorry?
The expansion of air molecules. When you're talking, when you're sending sound through the air, there's areas of compression and expansion. What are these areas of expansion called?
Troughs.
Good idea, good try. Any idea, Ajar?
Isn't it like thermal expansion?
You're close. It begins with R. If you guys remember this word, rarefaction. Do you guys remember that from our first weeks? Yeah. So whenever you have a longitudinal wave, the longitudinal wave travels by compressing some bits and expanding some bits, or whatever it's traveling through. Yeah. The compressed bits are called compressions. The expanded bits are called rarefactions. Okay. Notice the energy causing the compressions and expansions travels forward through it. If I speak to a person, the energy that gets to his ears has traveled because of these compressions and expansions, compressions, expansions. And my sound has also traveled in the same direction. So sound is longitudinal because the energy goes in the same direction as the travel of the wave. Okay, that's all you need to know at GCSE about longitudinal. But you need to know how it works in more detail with sound and earthquakes. Right, so an object makes a sound by vibrating. What it does, air molecules, look at how it does. This is a very good explanation. It compresses some and other bits are expanded, okay? And those vibrations make air molecules vibrate, and those vibrations end up at your ear. What I want you guys to do is, you don't need to copy this. I want you guys to copy these 3 points. Talk about sound waves and say, and make these 3 notes on it, okay? It's very important. This is our first bit. As soon as you copy it, let me know. Notice as well while you're copying it, this red bit that's moving represents a guitar string. The guitar string moves and pushes air molecules together, you see? Look at that. Look what it's doing to the air molecules. It's compressing them. And then those compressions travel through. Look at how compressions travel through. And you've got areas of expansion here as well, where there's no compression. Very interesting how that works. So look, it's compressing over here. Look, there we go. You've got this compressed bit, and my arrow's following it. The compression is traveling, traveling, traveling. I'm going to do that again. My arrow's going to the left. As it pushes under air, look at that. That bit of compression there is traveling, 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 traveling. And between compressions, you have areas of expansion. And so the energy is traveling forwards towards your ears. The whole wave is traveling forwards towards your ears. There's no up and down. Oopsie daisy, my bad, I'll go back to it. Copy, Nigel?
Yep.
Excellent. Which one are you on, Marco?
Hello?
Hello, Marco. Which one are you on?
Wait, what? My thing's glitched. I don't know.
I'm sorry. I'm sorry. We're just copying these blue things down. This blue, this green, and this red. Have you copied any of them down?
No, I can't see it.
You can't see it.
It's on like your old thing.
Oh, that's strange. Let me just do that. Let me share it again for you. If you can't see it, don't worry. In tomorrow's lesson, what I'll do, I'll give you extra time and you can, I'll make you, I'll sort it out for you, okay? Let's see if I can get it for you now. So that's weird. Is it your computer, Marco? That's a bit funny.
Yeah. Well, it's just frozen on your one of your screens. I don't know.
That's really strange. I don't know what's happening. So let me just share that again. Can you see it now?
No, it's still the same.
Still the same? Okay, so Marco, what I'll do, it's recording anyway, yeah? And when I see you tomorrow, I'm gonna go through it. So if you can just be patient, we've only got 2 minutes left anyway. So we haven't got much time left, okay? So those 2 minutes, I'll give them back to you tomorrow. Is that cool?
Yeah, that's fine.
Okay. Everyone else can see it, right? I think they can. Ohima copied?
Yeah.
Excellent. So all we're talking about, Marco, don't worry, you can listen to it while we go along. We've only got 2 minutes left. We're talking about sound and how it travels through the air as longitudinal waves. Now, we've got about a minute left, so I'm going to introduce you guys to what we're doing next week. We're going to talk about the ear. We're going to label the different parts of it, okay? I'm going to explain what's actually happening in our ear in a bit more detail, maybe, than this PowerPoint is doing. Okay, after we talk about our ear, we're going to look at how we can use sound to help us find the distances to different things. Sound's an amazing thing. Ships use sound, or ultrasound, type of sound, to find out how deep the ocean is. We'll watch a little video on this, on something similar. And then, after ultrasound, we're going to look at how it's used to image babies in the mother's womb. So doctors use this to find out the sex of the baby. Ultrasound can be turned into an image, which is really interesting. Sound, in a way, is being turned into light. And then earthquakes. We're going to look at how earthquakes happen, what the earth structure looks like, and also, let's skip this bit, we don't need this bit. We're going to look at the different types of earthquakes and how they shake the ground in different ways. Some of them make the ground go up and down. Some of them make the ground go left and right. Earthquakes are amazing because they've allowed us to figure out what's inside the earth. And we're going to talk about how that happens. We have not been deep in the earth enough to know that there's a core that's solid, or that there's a layer of molten magma there. We haven't seen it. We see it coming out of the earth sometimes, but we haven't been in there to see it. However, we can use sound waves to help us predict and figure out what's in the earth. Again, something to look at next week. We'll look at that. So guys, it's 6:15 now. Lesson's over. We had a glitch earlier where we stopped, where we basically had to break the lesson up into 2 parts. So what I done in that glitch, I took it off with the break, okay? So you guys had less of a break today, just so that you didn't have less lesson time. I hope you're okay with that. Is that okay, Hima?
Yeah.
Okay, well done. Am I seeing you tomorrow, Hima, at 3 p.m.?
Yeah.
Okay, well done. Did you learn from this lesson today?
Yeah.
Okay, have a nice day. Bye-bye.
Thank you.
Welcome. Audrey, you okay?
Yeah, thank you.
No problem, you're welcome. Any extra questions?
No.
No, okay, well done. Marco, I'll see you tomorrow at what time do I see you tomorrow? 2 p.m.?
No, I think it's at 6.
Do you prefer 6?
Well, I don't mind.
Okay, so just tell your mum I asked whatever time you wanted and you said tomorrow you don't mind 6, yeah? Is that cool?
Yeah.
All right, lovely, Mark. I'll see you tomorrow.
Alright.
Yes, are you okay?
Yeah.
Any questions?
No.
More star jumps today in the park? When are you going to go park again?
5 months.
All right, take care, Yasser. Assalamu alaikum.